Hello, welcome everyone. It is June 6th, 2025, and we are in another Noel discussion on Synergetics. This is Synergetics for beginners. We have some sections lined up. Noel, I know you have many things to discuss, so share your screen or request that I share mine, and thank you for joining.
Cool. I'm going to try and make Synergetics pretty easy to understand because anybody who's read through Synergetics sees it's a big book with lots of big words and it can be pretty daunting. I read in a book by Robert Anton Wilson. It said, everybody understands Mickey Mouse. Very few people understand Einstein. Almost nobody understands Buckminster Fuller. Now, I had Bucky's book at the time. That was probably when I was like, I don't know, 19 years old or something like that. And I would look through the book and couldn't really understand it, but didn't try too much. It was just kind of a novelty on my bookshelf. And I'd always planned on studying it. So, well, long story short, after studying it, I see that the math and the concepts are actually pretty easy to understand because the whole geometry is based on closest packing of same-sized spheres. So then he creates a bunch of different polyhedrons. Poly means many, and hedra means face. So this is a tetrahedron made with four closest packed spheres which have been extended to show the vector dynamics or the vector system. And there's 6 vectors connected in the 4 balls which make up the tetrahedron. Tetra means 4 and hedra means face, so this has 4 faces. Then you have like an octahedron, and it has 8 triangular faces, and it has 6 vertexes. And so the basic methodology of Synergetics is based on closest packing of unit radius spheres, and he considers the tetrahedron as the base unit of quantation for universe. Here's a picture here just showing what happens when we closest pack spheres. When we put one sphere next to 2 spheres, it creates this little triangle. And when we put that next to 3 spheres, it creates a bigger triangle. And we put it next to 4 spheres, it creates a bigger triangle, just like you were filling balls inside of a rack on top of a pool table. When you see it from this different angle, you can see that when you put one sphere, like this one, on top of 3, just like starting at the beginning, you get one tetrahedron. When you put those 4 spheres on top of the next bigger triangular plane, which is 6 spheres, you get this bigger tetrahedron, and it has 10 spheres. When you put these 10 spheres on this next layer of 10 balls, which is a triangular system of balls there, then it becomes this bigger tetrahedron, and so on ad infinitum. You keep creating bigger and bigger and bigger tetrahedrons. Bucky says of his system, about his entire book, all geometrical and numerical values derive from fractionation of the whole. And the whole he's talking about is the whole tetrahedron. We'll notice here in this 2 frequency, and on this note then, what Bucky calls frequency is how many intervals are between the total number of spheres on the edge length of any of the polyhedrons. This one here has 2 intervals between the 3 spheres, so it's a 2 frequency. This one has 3 intervals, so it's called a 3 frequency. You can equate the name frequency with the name size. You can also equate it with time. How many times can you create a tetrahedron with closest packed spheres? Well, the first time is with these 4 spheres, and the second time is with these 10 spheres, and the third time is with these 20, and the fourth time is with these 35. And so time is related to frequency. in Synergetics, and we'll talk about that a little bit more. Now, when he says all numerical and geometrical values derived from fractionation of the whole, what he's talking about is when we fractionate, for instance, this 2-frequency tetrahedron by truncating or fractionating off these blue balls from the vertexes, we create this internally shaped octahedron with 6 yellow balls creating the 6 vertexes, as I just showed up in the blown up model. When we truncate it at the 3-frequency level and knock off all these blue balls, we create the truncated tetrahedron with its 4 hexagonal faces and its 4 triangular faces. When we truncate the 4-frequency tetrahedron, we knock off these 4 balls on each of the 4 vertexes, and we get the 2-frequency or size 2 octahedron with its 6 yellow balls representing these 8 faces it has, octahedra. Now, when you knock these yellow balls off of the octahedron every 2nd frequency, it creates the green ball structure in here, which is the vector equilibrium. The vector equilibrium is also called the cube octahedron. It's called the cube octahedron because you kind of cube it, and I'll show you some more shapes in the future to explain the cube octahedron a little bit more. Okay, so from there, let's go ahead and take a look at this chart here. Hopefully this stuff will all pull up fast. I try to. And I'll show some more pictures in a second. I guess this computer's just going to go as fast as it can, so we'll be patient with it. So I drew up this chart to show the fractionation periodicities in association with the frequencies of the tetrahedron, by which the other 5 symmetrical polyhedrons exist inside of this matrix. Going to the left here then, after I took a big huge sheet of paper and took a pen and a ruler and drew up all these lines, I went ahead and of course filled them with the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., up to 144. You'll notice here that once again, when you add 1 sphere to 2 spheres, it creates a little triangle of 3 spheres. And when you add 3 spheres to that complex, it creates 6 spheres. So when you add the basic numbers as same-sized spheres, this is the process which universe uses to systematically coordinate real-world spheres and real numbers into triangular shapes. This is the formula to determine how many spheres are in any size triangle or any frequency. If you put 1 in, you get 1 to the 2nd power plus 3 times 1 is 3 equals 4, plus 2 equals 6, divided by 2 equals 3. So that's how you use these formulas. You put any of the natural numbers into this f function for frequency. If we put 2 in, we have 2 to the 2nd power is 4, plus 3 times 2, which is 6, equals 10, plus 2 equals 12, divided by 2 equals 6. And there you see the 6. This enables us to put in any number, and we can determine any size triangles, total number of spheres. There are also formulas which tell how many times these spheres touch. I don't have that written down on this paper. Now, as I showed you on the other pictures, when you take this 1 sphere and you put it on top of these 3, it creates a tetrahedron of 4. When you take those 4 and you put them on top of this triangle of 6, these 6 right here, it becomes 10. When you put these 10 on top of the 10 triangle, it becomes 20. And so the process that universe uses to systematically coordinate its closest packed unit radius energy spherics is by adding all the triangular numbers. 1 plus 3 equals 4, plus 6 equals 10, plus 10 equals 20, etc. Now, every second frequency or second time that you can create a tetrahedron with closest packed spheres, you can also fractionate it. Every second time you can fractionate by taking 1, for instance, on the first time, for a total of 4 off the vertexes, and it creates the 6 closest packed spheres of the octahedron. When there are 5 spheres to the edge length, it's a 4 frequency tetrahedron, and that has 35 spheres. If you knock 4 off of each side for a total of 16, you get the 19 remaining balls of the 2 frequency octahedron, or size 2. Now, when you knock off 1 ball from each of its vertexes for a total of 6, you get the 13 balls of the vector equilibrium, which is this little green figure in here. Now, as we continue fractionating it, we notice that on every third frequency, we can get this truncated tetrahedron, as I showed in that picture, and it shows up every third frequency at the center of volume. In other words, you couldn't take this 3 frequency and truncate it symmetrically and get the vector equilibrium or this 2 frequency octahedron out of it. Just like, it might sound silly, but you can't fractionate this 1 frequency tetrahedron and get anything out of it. So it's by symmetrically fractionating the tetrahedron that you obtain all these closest packed unit radius spheres as a model. Every 6th frequency is when you can truncate the tetrahedron. You take these 84 balls of the tetrahedron and you knock 40 off, 10 off of each of the vertexes, and you obtain 44 for the octahedron. When you knock 6 balls off of the octahedron's vertexes, you get the 38 balls of the tetrachedecahedron. I once again had created this whole chart before I had discovered these formulas. I discovered the formulas and equations later. If you put 1 into this equation, you get 38. If you put 2 in, you get 201, and etc. ad infinitum. Now, when you take these 38 balls and you truncate the vertexes, you get the 14 balls of the first size cube. The total number of spheres in the cube goes 14, 63, 172, etc. Now, the reason I made this chart, let's go ahead and close that out for a second. Was because Arthur Young, who was the only student of Oscar Veblen, and who Oscar Veblen in 1926 or so, he developed a relativity theory training class just for Oscar. Oscar was a student starting when Arthur was Oscar's student when he was 17 years old, and he entered Princeton, and he studied under Oscar Veblen, who's a world-renowned mathematician. After completing his course in relativity theory, he went on to study quantum mechanics and relativity theory and all those mysteries that were going on in all those different years. He studied Maxwell's equations, etc. The guy was real smart. I met him when he was 83. So the point I'm getting to is this older fella, right? He'd been studying this unified field his whole life. And when I was 22, I met him. He kind of advised me. He advised me that what was happening was these different total number of spheres. They were emulating. Do you have the section 419 available real quick? Where it shows the total number of closest packed spheres in the uranium and the molybdenum and the magnesium? I have it. No, I don't have it. You grab it.
419.
What's that?
419.
Yeah, here, I'll give you the exact one. I'm sorry.
All right.
419.21. So here's what I'm going to do also. I'll open up something that prepares me for what I was going to talk about also.
Yep. Okay, let me just... it just takes a second to get it on Zoom properly in a live stream, but it will be there in a second.
I didn't know that. It's okay. So here, while you're doing that, let me share a screen, and I'll talk about something else. Well, are you ready already?
Yeah.
Okay, go ahead. You go ready first. Boom.
I'm just going to share you This?
Go up a page. Yeah. So I don't know if people can see that, if you can make it bigger, but basically what Bucky's done is when you closest pack spheres in the shape of the cube octahedron, you take 12 and you put them around 1. And he calculated that if you did that, you get the total amount of nucleons in the magnesium by way of you have 12. And then if you put a icosahedral shell around that, you get another 12, which is, like, I can't see, but 26% of all the magnesium. He does the same thing for molybdenum, which is element number 42. And he shows how it has the correct number of nucleons. And then he does it for uranium also. Yeah, that's way easier to say, thanks. So basically, this is what Arthur showed me. And then he showed me page 99501, the vector totals. And while you're pulling that up, let me share, unless that's where, oh, cool, you can pull it. Just pull it 99501. So click on those little vector totals on the left there, either one. The second bottom one's better, bottom one. Sure, click. Oh, where you go? Oh, yeah, okay, that's good enough. Just go there. So basically, the total number of vectors, which are the interconnection points between these closest packed spheres, he adds all those up. And this is associated with what he calls vectorial modeling and his vectorial counting system. Go down a little bit, maybe. I don't know where he writes the words. Well, we won't worry about it. Let's go ahead and bump out of there. So basically, Arthur's showing me that what Bucky's doing is he's creating closest packed spheres and showing identifications to the atomic. What those are then, I'm sorry. So you have 2, 8, 20, and they show the total number of vectors in these vector models, which are identical to the most stable atomic elements. So the magic numbers associated with the stable atomic elements. Click out of that, maybe. I'm going to share a screen real quick with some stuff. Sorry if this is so boring, everybody, but it's actually really kind of easy to understand, which is, am I sharing?
Mm-hmm.
Oh, okay. Let me pull up what I wanted to pull up. So this just basically shows what Bucky's talking about. He's not talking about quantum mechanics because he thinks he's smart. He's been looking at this from a different perspective. He doesn't talk about Einstein's relativity theory because he thinks he's smart. My point is that Arthur told me that synergetics was Buckminster Fuller's attempt to create a unified field theory. And what he did was, in Arthur's opinion, was he was able to link relativity theory with quantum mechanics in an extraordinary fashion. Okay, so he is the one who told me we needed to study the higher frequencies, and that's why I drew this chart up. Little bits and pieces of what Arthur and I talked about came back to me as I started studying this stuff. What he told me was I needed to study around the 137 frequency level because he thought that the vectors related to synergetics were related to the T tensors from relativity theory. And this is where the momentum energy and the mega electron voltage for the system exists. So that's why I drew up this chart. Bucky says quantum mechanics commences with the totality of energy of physical universe, energy intertransformable either as matter or as radiation. So the scientist has a rigorous, I'll just read it. The child scientist's show opens with reiteration of rigorous science's one and only acceptable proof, experientially redemonstrable physical evidence. So we can demonstrated experientially over and over. So all of the scenarios proofs and their rationally interrelated number values derive exclusively from progressive equatorial symmetry halvings of universe's minimum structural system, the tetrahedron. Multiplication only occurs through progressive fractionation of the original complex unity of the minimum structural system of universe, the tetrahedron. And this is why Arthur told me to fractionate the tetrahedron and study those higher frequency levels. So rational, numerical, and geometrical values derived from the parallel and perpendicular halving of the tetrahedron. And then he explains all the geometries in the cosmic hierarchy emerge from the successive subdividing of the tetrahedron and its combined parts. So when you chop up the tetrahedron in different ways, like chopping up this way or trisecting it this way, you get all these different, you get the octahedron, you get the cube, you get the icosahedron, you get the rhombic triacontahedron, you get the rhombic dodecahedron, you get the e-quantum modules, you get what are called mites, which are the quarks of the system. And he's not being abusive of his attempt to illustrate the relationship between quarks and real-world nuclear physics. As he mentioned, he's trying to always have experiential proof. Here we see the tetrahedron broken up and fractionated into a truncated tetrahedron. It shows the icosahedron symmetrically facing one of its faces. Synergetics shows how we may measure our experiences geometrically and topologically, and how we may employ geometry and topology to coordinate all information regarding our experiences, both metaphysical and physical. So the mathematics involved in synergetics consists of topology. That's like the topological system of the polyhedron, as well as omnitopology, which is the internal system. So synergetics consists of topology combined with vectorial geometry. Synergetics derives from experientially invoked mathematics. Experientially invoked mathematics shows how we may measure and coordinate omnirationally, energetically, arithmetically, geometrically, chemically, volumetrically, crystallographically, vectorially, topologically, and energy quantum-wise in terms of the tetrahedron. So synergetics makes possible a rational whole number, low integer quantation of all the important geometries of experience, because the tetrahedron, the octahedron, the rhombic dodecahedron, the cube, and the vector equilibrium embrace and comprise all the lattices of all the atoms. So this is where his unified field, or the unifying everything, what do you call it? The grand, The tetrahedral and vector equilibrium models in the isotopic vector matrix provide an absolute accommodation network of energy articulation, including the differentiated proclivities of all these different behaviors in universe: your dynamic kinetic, your energetic synergetic, entropic and syntropic, gravitational and radiational, involuting and evoluting, etc. It explains vectors and tensors. He says vectors and tensors constitute all elementary dimension. A vector represents an expelling force, and a tensor represents an impelling force. So together, synergetics also integrates, the proclivities of inward and outward, three-way aroundness, processional processing. He is able to explain the intertransformative behavioral processes, phases of incandescent to liquid to plasmic to thermal to vapor. And he's able to measure and elucidate the disciplines of biological, chemical, cryogenic, and crystallographic. He explains electrical, genetic, geodetic, geological, mathematical, teleologic, scientific, etc. So he really is trying to explore for the comprehensive rational interrelationship number constants between all of these different sciences. It's a 1,300-page book. You should read it if you're interested. I'm just going over the basics now. So this is his grand synergetic hierarchy, his grand strategy. See, he was aware of a lot of different geometries going on at the time. And he says, although we are deeply and inescapably aware of the vast ranges of unexploited geometry, we must not permit such preoccupations to obscure our awareness of the generalized, comprehensively coordinate, arithmetical, geometrical, and factorial system employed by nature in all her energetic, synergetic, transformative transactions. With the general system's discovery of the tetrahedron as the basic structural unit of physical universe, quantation, we find that there's a fundamental hierarchy of vectorial geometric relationships that coincides with and integrates topology, quantum mechanics, and chemistry. And so I took him at his face value because I never studied any of these things before. First book I studied on any of this stuff really, other than I had read lots on lots of different subjects for many years. When I was 40, I got a hold of Synergetics, and when I was reading, I was remembering what Arthur said, and I just took Bucky at his face value. Bucky explains all of the exact sciences of physics and chemistry have been provided for the accounting of the physical behaviors of matter and energy only through separate, unique languages that require awkward translation through the function of the abstract interpreters known as the constants. But Synergetics now embraces the comprehensive family of behavioral relationships within one language, capable of reconciling all the experimentally disclosed values of the XYZ CGS mensuration systems adopted by science, and that's your centimeter, grams, and seconds system. The adoption of the tetrahedron as mensural unity and the recognition of the isotopic vector matrix as a rational coordinate model are all that is needed to reveal the implicit omnirationality of all chemical associating and disassociating. Thus, we can provide a single language to recognize and accommodate Avogadro's law of gases, Bohr's fundamental complementarity, Boltzmann's operational procedure, Brouwer's fixed point theorem, Gibbs' phase rule, field equations, Einstein's energy equation, Euler's topology, points, areas, and lines, Kepler's third law, Newton's theory of gravity, Paulink's chemical structuring, Pauli's exclusion principle, thermodynamic laws, and L.L. White's point system. So these are all the things that he is unifying before I ever met him, before I ever read it. All those different fields of science are being unified in Synergetics. Now, it seems to me after studying this book that it's obvious that Oscar Veblen's favorite student, right, who's real into this stuff, knew what he was talking about when he told me this was Bucky's attempt to unify relativity theory with quantum mechanics. He said one of the reasons why he didn't think that it became studied was, one, because Bucky was against the established quo in the wars and all the power structures. And he writes about how these problems on planet Earth occurred, and they don't want to teach about that in academia because they want to program the kids in academia to do what they're told, get your job, be a lawyer, make sure you follow the law, be a banker, make sure you understand what you're doing, be a yada, yada. And so you specialize in all these different behaviors and you don't pay attention to how the whole system of unit Earth works with all of its different parts. Well, the other reason is because, and here's the most probably important, is because Bucky didn't prove, because the fine structure constant is at the heart of this whole matter. Feynman and others have said, nobody understands where the fine structure constant comes from. And that's why Arthur told me he thought that if we studied the vector totals, which are related to the T-tensors in relativity theory, we would be able to find the energy momentum by way of mega electron voltage in the proton. And that's why it's so fascinating that when I studied those higher number patterns up here, I'll just show you the screen again, I guess. That when I was up at the 137 balls to the edge length, which is 137 frequency, I got all these interesting numbers in there. Like I have 2,571,216 vectors are in this tetrahedron right here. And this number here is equal to 137 times 9,384 times 2. Well, 137 is the inverse of the fine structure constant. 938.4 is the mega electron voltage of the proton, according to page 39 of the book called Particle Physics by Frank Close. And so when I first saw that, it was way after I made this chart, and it was I made this chart before I even knew what mega electron voltages were. And it was only after I was studying nuclear physics that I kept remembering what Arthur told me about studying that 137 frequency level. So let's go back then to just talk a little bit more about maybe some pictures on this stuff. This right here is what's called a one frequency cube. It has 14 spheres. These same. Oh, okay, it's not doing it. Here, hang on. Thanks, Brian. Zoom is currently using your camera. Yeah. So as I showed on the chart, the cube only shows up every sixth frequency. The first time you can make a cube is with these 14 spheres here. You take these 10 and you just put one sphere here, like a green one here, another green one here, and another green one here behind it. And then you cock it up onto its side, and then you put another green one right underneath here. So basically, when you put 8 spheres on the 8 faces of the octahedron, you create this first cube in accord with closest packing of unit radius spheres. The second time you can make it is with these 63. Oh, good, I did put it. And so you'll notice that here's the 4-frequency tetrahedron. I've turned it up onto its edge to show its size relationship. This is the 4-frequency tetrahedron, and you'll notice it's got these 4 spheres running through. It's diagonal. I mean these 5 spheres, which is the 4-frequency tetrahedron. So the 4-frequency tetrahedron lies at the heart of the 2-frequency cube, even though that 2-frequency cube doesn't show up until right here at the 12-frequency tetrahedron, where you truncate that tetrahedron and you get the 63 spheres inside of it, which, as I just mentioned, has these 35 spheres from the 4-frequency tetrahedron inside of it. So all these different equations then become realized as symmetrical equations. Thanks for your patience. So when we closest pack unit radius spheres like that, the tensors are those spheres that are connecting. And this is the equation for those total number of spheres. Once again, if you put 1, 2, 3, 4, etc. into the F and do the equation, you get the total number of the spheres. The total number of kissing points between those spheres is what's called the vectors. And this is the vector total. And this is the whole rational unit amount of volumetric space inside of the tetrahedron. I'll explain a little bit more how the tetrahedron acts as a unit of volume and why all of these then, as they are symmetrically fractionated, create these symmetrical equations. This is the octahedron spheres and vectors, or kissing points, and their volume. When they have the same edge length, the octahedron always has 4 times as much volume as the tetrahedron. The vector equilibrium always has 20 times as much volume as the tetrahedron. The cube always has 24 times as much volume. The tetrahedron has 96 times as much volume, and the truncated tetrahedron has 23 times as much volume. And so it's interesting to see that this volume ratios in whole rational units also relate to the symmetrical fractionation periodicities, which create these symmetrical equations. Now, scientists in academia don't know about any of this. This is not listed in Synergetics. These are all minute observations. Now, we link these. I guess I'm not going to be doing beginning Synergetics at this point, but we link these then by way of first understanding what the ratio is, so that we can use these economically in order to teach children how to ratio, for instance, a tetrahedron or an octahedron without having to use the difficult to use mathematics that's used in XYZ math right now. So these polyhedrons all enclose whole rational units of tetrahedral volume, as distinct from the irrational cubic volumes associated with our current XYZ system. The translated volume formulas all follow ratios which are related to frequency to the third power, or edge length to the third power. These volume ratios enable children to more easily and quickly ascertain the cubic volume associated within the XYZ cubical mensuration system as follows. So the edge length is the frequency. So if you just get out a ruler and you measure the edge length, you multiply the edge length of any of these polyhedrons listed above to the third power, then you multiply this by the Synergetics constant of 0.11785, which is the inverse square root of 72. For an example, if you got a 2-inch edge length tetrahedra, first you go F equals 2, and that's 2 to the third power equals 8. The constant, next multiply by the constant 4, because the volume is 4 times frequency to the third power. If the frequency is 2, you put 8 in there, and you multiply it by 4, and you get 32. So that's where you get the 32 volume. Next, you multiply it by that Synergetics constant, 0.11785. And then you get 0.37712 cubic inches of volume. So those 3 steps, multiply the edge length to the third power, multiply it by 4, multiply it by 0.11785, saves you from having to do some more difficult to understand computations. In Synergetics, Bucky explains let's see, I think it's wrong pages. Sorry, I guess I don't know where it is. It's farther down. Here it is. So in Synergetics, I think this is 990. Bucky explains how triangles and tetrahedrons accumulate themselves in second and third power progressions by way of number pattern theory, identically to the way that the square and the cube accumulates itself in accord with second and third power rates of progression. A guy named Alfred Korzybski, he's a semanticist, he said, words cause conditioned associations and mechanical reactions that keep our minds locked into specific realities. With that in mind, mankind's mind is locked into the reality of the words associated with squaring and cubing. 1 squared is 1 square area. 1 cubed is 1 cubic area. Down on this cube here, 2-inch edge length, for instance, 2 squared gives you 4 squared, 2 times 2. 3 squared gives you 9, 3 times 3. So when we think about 3 to the second power, 2 to the second power, or 1 to the first power, we think in terms of squaring 2 to the third power, or 2 edge length, 2 width, 2 height equals 8. So 2 times 2 times 2 is 8, 2 to the third power. But we call it cubing. And what mankind's not aware of is that the triangles accumulate themselves in the same way. You have 1 triangle, and then when you have a 2 edge length triangle, you have 4 total triangles, just like there are 4 total squares. This takes up less area than this one does, but it's still whole rational units. You'll see when we have 3 edge length, we get 3 to the second power is 9. So second powering is not necessarily squaring. It could be considered triangling. And third powering is not necessarily cubing. As we can see here, when you have a 1-inch tetrahedron, you have 1 tetrahedral volume. When you have a 2-inch tetrahedron, you have 8 tetrahedral volume, and he shows how that works down here. We'll see that in making this closest packed unit radius sphere isotropic vector matrix agglomeration here, you have 1 tetrahedron on top of 3 tetrahedrons which surround an octahedron. Remember that octahedron has 4 times as much volume as the tetrahedron with the same edge length. So this is one edge length, and that's 1 inch edge length, for instance. That's 4 volume. Add the 3 tetrahedrons for 7 plus the one on top, and it gives you this 8 volume. That's 8 total volume when it has an edge length of 2 inches. When it has an edge length of 3 inches, we would say it has 27 tetrahedral volume, and this has 27 cubic volume. This has 64 cubic volume, and this has 63 tetrahedral volume. So we've used words to associate second and third powering progressions of universal affairs only in terms of the cube, and that is maybe one of the reasons why we still continue to use only the XYZ Cartesian coordinate system. Well, notice that when we closest pack spheres into a hexagonal array, they actually accumulate in the same volumetric totals that the tetrahedron does, where we have one sphere, and then we have 6 closest packed around 1, which is 7, and then we have 12 around 6 around 1, which is 19, and then we have 1 with 6 and 12 and then 18 packed around it for 37. When we add those together, we get the same volume total. So if you create a hexagonally closest packed spherical array, it will array itself out in third power progressions of volumetric consideration. Now, here, let's just chat a little bit. Does that kind of make sense so far about what I'm talking about and stuff, as far as yada yada? How the different tetrahedrons are being fractionated, and you get the different polyhedrons inside of it. Does that kind of make sense? Can you hear me, Daniel?
Yeah. I'm thinking of what to ask. What does it mean that all of these natural ratios related to the empirical difference in mass energy of all these particles, what does that mean? Is this a configuration that is somehow stable or special in some way? Could multiple give existing physics?
Yeah, let's talk a little bit about structural stability. When Bucky was a kid, he was given some toothpicks and some peas, and he started making different structures, but he couldn't really see very good, so he was just putting them together the best he could. And what he did was he made what's called an octahedral tetrahedral trussing matrix, which might look like the bottom of this structure here, and also then would look like this structure here I'll show. So the octahedral trussing matrix that he made in school was this little tetrahedron next to this octahedron, next to this tetrahedron, and this upside down tetrahedron, next to this octahedron, next to this tetrahedron, and this upside down tetrahedron behind it, and this octahedron. So he created this parallelogram made of tetrahedrons and octahedrons, and this is called the octahedral tetrahedral trussing matrix, and that's the key to the trussing matrix inside of the isotropic vector matrix. He made up something called polygonal necklace. Is that shown on the whole screen there?
Yeah.
I only see you, but it's okay. If the screen's showing me, that's good. So you'll notice how this complex here I made with toothpicks and rubber bands, and I taped the toothpicks together. There are 24 toothpicks. I taped them together in stable triangles. See, Bucky was feeling his way to be able to put those peas together in those toothpicks so he could just create a structure. And he created a tetrahedron, and then he connected that to an octahedron and another tetrahedron and made that matrix. Because he couldn't see real well, so the other kids were all building straight up as squares. So what he realized then, and he remembered later, was that the triangle is the only structure that holds its shape in association with vectors and tensors. See how the tension in the system is a rubber band. It's creating tension. And that tension is stopping these three vectors from doing anything other than maintaining their structured triangular shape. So that's what Bucky talks about as structure. Self-stabilizing, intertriangulated, polygonal and polyhedral continuums. Now, this is his intertransformative mechanism, and what I'm showing you now here is the square face. See how if you were to take these three vectors and put another vector inside, you'd have four vectors connected. If you did it again and you had five vectors connected, or 6 or 7 or 8, no matter how many you put in, it would always just be kind of like a polygonal necklace. See, because it doesn't hold its shape. The square doesn't hold its shape when only held by vectors and tensors. The pentagon does not hold its shape when only held by vectors and tensors. The hexagon, the septagon, the octagon, etc. The only shape that stabilizes itself is this triangle when we think about vectors and tensors. Now, the vectors once again represent the T tensors in relativity theory, and the tensors are the R tensors from relativity. That's what tells the system how and when to curve and how much to curve. That creates the angular momentum of the system. Okay, so if you want to make one of these, you just take the 8 triangles and you just get another piece of tape and a rubber band and you connect the 4 triangles together like you see there. And then you do it again in duo because there's 8 triangles. Put the one set of triangles on top of the other triangles and just interconnect then 4 of the vertexes of that little square and triangular field you made, and then you'll be able to make the structure. So this is the external shape of what's called the cube octahedron. You see it has 6 square faces and 8 triangular faces. The square faces enable the stable triangles to articulate the proclivities of its spin domain. Let me hold it different, maybe it'll spin easier. So that it can spin into and out of the various polyhedral shapes, such as, sorry, I just made this the other day, so it's not. So here it works. So from the cube octahedron, it shifts down into the octahedron. At a midface here, if you were to take these 6 square faces and place 6 vectors between the diagonal, it would make 12 faces out of those 6, and they would all be the same size triangle. And you add that to the 6 faces, and you would then get the icosahedron. Icosa means 20, and hedron means faces. So from the vector equilibrium, it goes to the icosahedron, and then it goes to the octahedron. It spins out to this 7-volume thing, which we just looked at with 3 tetrahedron around an octahedron, and then it spins flat. It can go into a negative tetrahedron, which is quadrivalent, meaning there's 4 vectors per edge length, and it can flip up into another oppositely oriented tetrahedron. So this just shows the intertransformative mechanistic means that energy quanta, in accord with his vectorial energy accounting, enables the movement, the movement of the vectors in such a way that it can transform itself into the different shapes. So that shape we're seeing is at the heart of the vector equilibrium. That vector equilibrium is at the heart of the tetrahedron. Maybe I'll show you that again. Here I just want to show how the tetrahedron here can shift phase it out simply by sliding, and then it's 2 face bonded tetrahedron. Slide back in, 1 tetrahedron, slide out, it becomes 2 face bonded, so 1 turns into 2, it doubles. Then it spins out to the octahedron. 2 becomes 4. Now, what's interesting about this model and the mathematical equations that I developed, we'll jump back on that screen and show a little bit of the intertransformative mechanism. You'll notice here that, for instance, this has 6 edge lengths, even though they're bivalent, meaning they have 2 vectors per edge length. This has 12 edge lengths. It has 6 vertexes. When it expands, it has 12 vertexes, and it has 24 vectors. So we notice a doubling of the vertexes and a doubling of the vectors. What's interesting about that is that Bucky had not discovered, am I sharing now? Okay. Bucky had not discovered, he didn't write up this big chart. This chart's not in Synergetics. This should be like in this chart should be on the high school walls and math walls, and the kids can look at how all these numbers develop and understand that 6-axis metric. But what he didn't discover, of course, is these equations on the left-hand side, although he had maybe a few of them. He had like these volume formulas down here for sure. So he didn't notice how the transformation process worked in an arithmetical and algebraic fashion. So kind of, for instance, when you look at some of these different polyhedrons, you can notice that the different vectors and tensors and volumes all transform themselves one into another in accord with whole rational units, or in accord with at least basic mathematics. Let me explain. We just saw how the 6 vertexes turned into 12 by doubling, and how the 12 edge length turned into 24 by doubling. But let's look at some of these different mathematical equations here, and I'll show something very interesting. Look at how the total number of vectors in the octahedron is equal to 4 times frequency to the 3rd power plus 6 times frequency to the 2nd power plus 2 times frequency, so that you get these numbers. We just saw the 12, right? Now let's go ahead and look at this equation right above. Do you see how it's almost identical? 4f to the 3rd plus 6f to the 2nd plus, wait, it changes by 1f plus 1. So you see this here, 3f plus 1. You see this just ends at 2f. So if you add frequency plus 1 to the total number of vectors in the octahedron at any frequency, you'll transform those total number of vectors into the total number of spheres in this cube. For instance, frequency is 1, so if I add frequency plus 1, which is 2, to 12, I get 14. So if I add, this is a 2 frequency vectors in the octahedron. If I add 2 plus 1 or 3, which is frequency plus 1.
Why add f plus 1? What's the relevance of the f plus 1 differential when the difference between the two equations is 3f plus 1?
Oh, go ahead and add f to 2f, and how many f's do you have? If I have 2 dogs and I add 1 dog to it, how many dogs do I have? I have 3. If I have 2 f's and I add 1 f to it, how many f's do I have? 3.
But you highlighted that these two equations differ. Oh, okay.
Sure.
I'm
glad you follow me, because I want to go slow and make sure everybody understands. It's kind of real basic, but it's hard to see. See how this is 4f to the 3rd, 6f to the 2nd, 2f.
Okay. I was looking at the wrong row. I see it now. Yes. Okay.
Does that make sense? So if I add f to this, it'll be 3f. And if I add 1, it'll be 3f plus 1.
Yeah.
And that is this equation. And that plays itself out by adding 2 to this one to get 14, 3 to this one to get 63. Whoops. You add 4 to 168 to get the 172. You add 5 to 360 to get the 365. And you add 6 to the 660 to get this 666. So you got 660 vectors here, 666 there. So now we can look at how the volumes also transform themselves, for instance, into the vectors and or the spheres. And what I'm showing then is, see, what he thought he made, Bucky thought he made a, a realistic understanding of quantum mechanics, which is how the energy vectors and the gravity tensors intertransform themselves at the very smallest unit of structure in order to create these different structured patterns. So when we take this volume of the tetrahedron, it's the same as the volume in what we think about as the cube. 1 to the third power, 2 to the third power, 3 to the third power, 4 to the third power, 5 to the third power. When we take every odd frequency, like 27 or 125 or 343, and we add 1 and divide by 2, we once again get the cube's spheres. So this shows how the volume ratios transform themselves into the spheres in accordance with basic math. 27 plus 1 is 28, divided by 2 is 14. 125 plus 1 is 126, divided by 2 is 63. 343 plus 1 is 344, divided by 2 is 172. And 729 plus 1 is 730, divided by 2 is 365. So what I'm showing then is how the basic agglomeration of closest packed spheres, their kissing points, right, as energy units and gravity tensor units, are intertransforming themselves in association with their whole unit volumetric internal ratios, all in accord with these basic mathematical formulas. So these formulas, they take the place of the Hamiltonian quaternions. You see, notice below how frequency takes the place of the imaginary component I within the complex number A plus BI, as it is associated within Synergetics binomial equations. Now, this occurs in the same way that frequency takes the place of the imaginary components I, J, and K within the Synergetics quaternion equations. So our computer programmers use the I, J, and K as rotations in their maybe not their coding, but in the way that they're programming their computers. And this enables them to rotate three-dimensional images on a two-dimensional screen, and then they can rotate things like arms and heads on robots. So we notice how the computer programming experts use I, J, and K as rotations, and notice how that when we translate the I, J, and K rotation variables for frequency, this shows us how universe uses the synergetic symmetrical equations to ratio the cyclic rotations of EMR at the quantum level of polyhedral structuring. And that's why we can derive all of the correct megaelectron voltage of the various particles in association with Planck's constant, the fine structure constant, and the gravitational constant in whole rational units. So in synergetics, this is synergetics equation for the total number of points, or closest packed spheres, on the surface area of the tetrahedron. 4f to the second power plus 2 is the total number of points on the octahedron's external field. 10f to the second power plus 2 is for the icosahedron or the cube octahedron. Now let's take a moment to look at how these are related. We have a plus bi is related to the complex numbers associated with the infinite number of imaginary points upon the surface of the imaginary circular plane. In synergetics, we have 2 plus 2 times frequency to the second power, or we have 2 plus 4 times frequency to the second power, or we have 2 plus 10 times frequency to the second power. And those are the total number of real accountable points upon the surface area of these different polyhedral spherics. So we're taking the imaginary out and replacing it with these synergetics equations, replacing the complex numbers. Bi plus Cj plus dk is related to the quaternion vector equations, wherein we have an infinite number of directional vectors connecting the center of gravity of the sphere with the theoretically infinite number of points upon the surface of the sphere. And in synergetics, where's the rest of my? So see these vector equations here? 24, it's a three-part equation. F to the third, F to the second, and F. Those are the total number of vectors. So in the quaternions, we have B times the I, C, J plus dk. In synergetics, we have B times frequency plus C times frequency to the second power plus D times frequency to the third power. And this is the total number of real accountable vectors, which we were just showing you. which interconnect the real accountable points in all physical structured polyhedrons. Then this other equation is related to the quaternion equations and the infinite number of imaginary points upon the surface of the hypothetical four-dimensional hypersphere. That becomes identical to the translated equations, which represent the total number of spheres. We see them in their opposite order here, so that you'd have A plus BI plus CJ plus DK. A becomes translated as 6 divided by 6, right? B is 25 and I becomes F. C is 42 and J becomes F squared. D is 23 and F then becomes the K. So the IJ and K axes are represented within these variables associated with these different symmetrical equations from Synergetics. And this is something basically new for all mankind's mind, if that interests them. Let me go down now here. Let's see if I can explain something a little bit better about some stuff. See, this is a really kind of a nice picture here. And this shows how when you closest pack unit radius spheres, you get these different sized polyhedrons. Remember how I just showed you that the 1-inch tetrahedron has one volume? In association with that, if you were to take the diameter of the cube octahedron as 1 inch, it has exactly 2.5 tetravolume. And if you were to take a diagonal of the cube of 1 inch, it would have 3 volume. The octahedron, the rhombic tricontahedron, the rhombic dodecahedron, the cube octahedron, the cube, the truncated tetrahedron, the pentagonal dodecahedron, and the tetrachydecahedron all become rational whole units within that system of measurement of Synergetics. That whole rational unit measurement of Synergetics then shows how in our regular math, how much of this to show right here? If we have a 1-inch edge length cube and we measure a 1-inch edge length tetrahedron, we have 0.11785 cubic volume. This is all academia correct numbers. If you have a 1-inch octahedron, or we're using 1 meter here, but 1 meter octahedron, you have 0.714, 0.4714, etc. cubic inches of volume. So see how these are irrational numbers? They're not whole rational numbers like what happens when you use the tetrahedron as the base unit of measurement. If you were to take this number here and multiply it by 4, you'd get this number here. If you take the tetrahedron's number here and you multiply it by 20, you get this number here. If you multiply it by 96, you get this number here. When you multiply it by 23, you get this number here.
Let me ask a question.
Yeah.
What fraction of the way do you believe that system is complete? Like, do you believe that you have discovered n, or described or discovered, however the ordering is, n equations from a set of m equations? Or do you believe that it's mostly or only partially understood some of these relationships?
I'm not sure your first real part of the question, but I think that we and I don't understand the full ramifications of all these relationships. Like it was just 2 years ago that I met some folks who were interested in the quaternions, that I studied the quaternions, that I realized, oh, these are symmetrical to my formulas. And that's when I made these most recent associations. So I think there's millions and millions of associations related to real physical structure. Any real physical math that works in a real way must probably be able to be associated in some way with this isotropic vector matrix. Remember, Bucky said that he truly believed that he had discovered nature's own coordinate system. So once again, that's what that Arthur fellow told me. He says, man, you know what? Study these higher frequencies, because when we showed that 1 and 12 and 42 and 92 total agglomeration of spheres, which were related to uranium, molybdenum, magnesium, and hydrogen, he told me, this is a nice model, but we know that the atoms are not things like that. We know there's not just 92 somethings packed together, because they're vibrations and they all operate, every atom operates on its own individual frequency. And so Bucky has learned a way to model frequency. And he modeled frequency by the way of the tetrahedron. And the way he did that was by fractionating the tetrahedron.
Yeah. The tetrahedron is a mnemonic and an integrating nexus in theory and in practice and in actuality for all of these associations. It's like the Grand Central Station.
Right, right. All geometrical numerical values derive from fractionation of the whole minimum structural system, which is the tetrahedron. So, what were we just talking about before I bounced into this? Oh, well, here's anyways one thing. The reason there are whole rational units, all these different polyhedrons, is because they're made up of exact quantized units of this, either the tetrahedron, which is 1 volume, or the octahedron, which is 4. And so when I'm symmetrically truncating this tetrahedron, for instance, if you knock off all these blue balls, you get this 3-frequency octahedron designated by these 6 yellow spheres. You'll notice that inside this metric, all of it is octahedrons and tetrahedrons. When you truncate these yellow spheres, or the vertex of the 3-frequency octahedron, and every next 3rd frequency, you get this tetrachedecahedron in it, which is shown by these green balls.
Yeah, but just one quick thing I'll say on that. That's kind of like by doing certain symmetric operations of reduction on a tetrahedron, you get the ability to form all of these other integer accounted specialties. However, that can only happen at certain frequencies of resolution. Whereas if we're working with a block of granite that's a meter across, the number of molecules is so large, it can be approximated continuously. And so shapes can be chiseled using like a water jet. This could really happen. But there's a discretized form of this geometry that is a meshwork, and only at certain frequencies do certain reduction operations become yielding certain shapes, and certain equations jumping across levels in certain ways.
Yes, and that is why I found it so fascinating that when you fractionate the tetrahedron every 2nd, 3rd, 4th, or 6th frequency, you get these different polyhedrons inside of it. Every 12th frequency, because 2, 3, and 4, and 6 become common denominators for 12, all of the polyhedrons all show the same symmetrical center. They all have the same ball at its center of mass and center of volume, which is what this shows as it's expanding, even though this is the 6th frequency. This is what Buck is showing. Oh, where was it? Next page, sorry.
I see that as the conservation of the center of gravity with these symmetric reduction operations that maintain certain create and destroy certain symmetries in their symmetry, however, have the same omni-centroid. They're all aligned on their center of gravity.
Yeah.
With a certain spin.
Right. Now, I made that complex there, but before he does that, he just has the ratios correct. Right here, we have 12 spheres packed around 1. You can kind of see that 1 here with this line right here. And he's showing then how all these volume sizes and ratios are interconnected, as I just showed you out here, 1, 2.5, 3, 4, 5, 6, etc. But see, this is what he's talking about here then. This is the Synergetics isometric view of the isotropic vector matrix, and its omni-rational low-order whole number equilibrium state of the micro-macro cosmic limits of the nuclearly unique symmetrical morphological relativity, right? So it morphs into different things. So this morphological relativity, along with its interquantitative, intertransformative, intertransactive, expansive, contractive, axially rotative operational field. See, this may come to be identified as the unified field, which, as an operationally transformable complex, is conceptualizable only in its equilibrious state.
Let me give a short comment on that. So, we can understand that equilibrium state as kind of like the center of mass of a distribution conceptually. And what in that last quote you read, it's an operationally transformable concept that is a generalized field, because these pre-frequency relationships have certain connections with frequency-based relationships, which gives a sort of mapping or transpose with different kinds of systems phenomena, and one where the ratios of things that are just related to packing spheres recapitulate natural equations and patterns in a way that relate some of the specifics of our world, like physical structure and mass energy values, specific discretized values in our world, like quantum phenomena, are mapping to quantized, discrete vectorial geometry, all based around the TET and the close packed spheres.
Correct. Now, I didn't realize time was going. So here, let me kind of. So what was so fascinating of this intertransformative process that I just showed mathematically a little bit, we're showing how the basic systematic coordination of spheres creates these different types of shapes and whatnot. So at these specific frequencies, when you fractionate, you get all these different polyhedrons. And because Arthur told me, and then he wrote in his book, it's still unknown today why 1/137, sorry, man. It's still unknown today why 1/137th of the amount of angular momentum remains free and unconserved during the processes that creates electrons and positrons, protons and neutrons. And so when I studied this map and I noticed that this is 137 frequency right here, when you fractionate it one way or the other, it becomes divisible by the prime numbers, which factor into the total number of protons and neutrons and their values in association with real world structure. So I said to myself then, so this is fractionating the same way it fractionated every second frequency. Now I'm just going to fractionate it every 137 frequency. Let me see if this next page will come up quickly for me. And so when I did that, I made this chart here and showed what it would look like if I continuously fractionated in whole rational units 1/137th off of what's thought of as the angular momentum of these continuously expanding polyhedrons. And when I did that, I got this continuous number pattern, right? 137 times 1 plus 1 or minus 1 equals 136 or 138. When you keep doing this, what happens is that so let me start beginning. 137 times any number plus that number will be divisible by 23. 23 times 4 is equal to 92, and so you have 92 naturally regenerative elements, so 23 is the prime factor in 92. 17 is the prime factor in 1836, which is the mass proton electron ratio. When the electron weighs 1, the proton weighs 1836.152. We're only using whole rational units because of the system, so whenever you multiply 137 times any number and subtract that number, it becomes divisible by 17. And I asked myself, well, when do these numbers meet up, if ever? And when I noticed that they meted up here, at this point here, 9384, I did not know that this was, in accord with page 39 of Frank Close's book, Particle Physics, the megaelectron voltage of The proton, I only learned that later. I made up this chart before I understood mega electron voltage. I was just trying to find all the number patterns that Arthur was kind of talking about. What happens when you fractionate 1/137 off of the continuous expansion of these tetrahedrons? Well, they create these different points. Not just this only point, but look, it does it again. 137 times 36 plus 136 is equal to 137 times 138 minus 138, and that equals 18,768. Now we're going to get real fun here. I'll try and be real brief. I don't know if you're a bit hurry. So, after years of studying quantum mechanics, nuclear physics, and whatever, all these different books, I finally came to understand, we won't go through this, but people can stop the thing and look. So I wrote this paper here, Understanding Synergetics, Quantum Mechanics in the Unified Field, just recently. And there's all the different chapters in it. What I'm going to get to now, then, I'm going to go ahead and move right forward to the number patterns which are associated with this whole metric at these different fractionation periodicities. And like I said, I'm going to try and go relatively quick, so I don't want to. I'm going to start with something that Feynman's talking about. So Feynman explains to colleagues that there's a huge unknown with this mysterious number 137. See, the number is the value of the defined structure constant. It's actually its inverse, which is defined as the charge of the electron squared over Planck's constant times the speed of light. Okay. He says this number has more significance in the fact that it relates three important domains of physics: electromagnetism, quantum mechanics, and relativity theory. So since the early 1900s, physicists have thought that this number might be at the heart of a grand unified theory, which could relate the theories of electromagnetism, quantum mechanics, and most especially gravity. However, physicists have yet to find any link between the number 137 and any other physical law in the universe. So a guy named Dr. James Gilson, he talks about how Feynman asks, is the fine structure constant related to P, which is the perimeter of a polygon, the perimeter length of a polygon. And so I show how I just did on the perimeter edge length of the tetrahedron. When the perimeter length right here in the middle is P137, it has 137 spheres to its edge length, and this equals the inverse square of the fine structure constant multiplied by the proton, MeV, plus 1836 electrons, MeV, which is this number here. Proton plus 1836 electrons of 0.511 times the inverse of the fine structure constant times 10, and there's that 2,571,216 vectors I was telling you about. So the three scales then enable this different process wherein if I multiply that 9384, the first 0 point, by 720 degrees, the 720 is significant because that's the total number of angular variation on the external surface area of the tetrahedron. We get this number here. This is the fifth 0 point of my Penn scale. I only showed you one of my scales, that's the alpha scale. Now, when you divide this number by the quanta scale's 0 point, you derive 0.999455, and this is the difference of 0.000544, which is the electron's exact atomic mass unit. This shows us how universe can use two continuously halving or doubling frequencies to ratio one electron between them, thus enabling proton and neutrons to shift back and forth into one another by exchanging the one electron's AMU. And this accounts for what's called the weak force interactions. This is how and why the different proton and neutron are exchanging the electron in order to transform themselves. Now, when the tetrahedron has 919 spheres to its edge length, it has 776,150,640 total number of vectors. When you divide those total number of vectors by the same fifth 0 point right here that I showed of the Penn scale, that equals 114.875. And that's basically identical to the mega electron voltage of the up quark. There's a huge margin of error ratio on those. And this is from Andre McCaw's work. Codate is basically just about double that. So if you double that, you get codate as MEVC squared for the up quark, 2.3. mega electron voltage. And then when you multiply that by 2, you get 4.5, which is then the mega electron voltage for the down quark, according with McCaw's work. It's about 4.8 according with co-data, but there's a huge margin of error difference. So that shows how we get the quark values. It shows why the nuclear.
Can you just go into the last little bit? A lot of the
Yeah, that's
details, so it's good for the paper, but just give a last remark and then we'll end it.
cool. So basically then that gives you your quark values. And then at the next stage, at the edge length of 3677 spheres, you can take that quanta zero point, which is related to that, and you can divide that by Planck's constant minus 1 divided by 2 times 2 to the 7, or that equals 360. And then you get the proton and the neutron's mega electron voltage. And so basically, a long story short, is that Bucky had discovered a way which nobody had followed, but which my teacher told me to follow, which may enable us to then unify the gravitational constant, the Planck's constant, the fine structure constant, the mega electron voltage of the proton, the neutron, the electrons, the positons, and both the up and down quarks. And that's kind of freaking amazing. That's really the whole long story short of it. Well, I don't know that was Synergetics for beginners, but I think the beginning really gave us a good idea of how all those different number patterns are interrelated and how people can see the basic buildup of structure by self-stabilizing intertriangulated polygons and polyhedrons, and then fractionating them at certain specific frequencies so they still have whole rational units of all these vectors and tensors, which then enable us to calculate these different mega electron voltages and the ratios to Planck, alpha, and gravitational constant. I think it's pretty amazing. And so, well, thanks for doing this lecture with me. I was trying to just get my mind stimulated because I'm trying to write kind of like a foundation paper. A friend is trying to help me get something published, and well, wish me luck on that. And that's about it. I'm glad you gave me the time to do this. I hope I explained stuff well enough.
Thank you. It's very thought-provoking. There's a ton I could say. A lot of it really something to look at the paper and look at the tables, and as we've discussed, work on the code that generates the numbers and visualize the relationships, do different kinds of analyses, and explore that mystery of the 137 and the relationship of all of these values.
It's pretty fascinating, though. Yeah. Yes. And I know it's super boring, so anybody that went through this, hey, thanks for paying attention. Maybe that will add something to your mind. I always think more minds entering into the system will be able to then make more correlations, because I got a finite mind, and it's kind of thousands of people learning about this could put thousands of different connections together, whatever they're studying. You know what I mean? I think it's pretty fascinating.
It's amazing, and there's a lot to say, but that's great to end it. So thank you,
Thanks
Noel.
for having me.
Peace. Bye.
Take care, buddy.